Okay, we'll get started with today's class. A little bit. A couple reminders before we start. So first, just remember that the stuff that we're covering today is not on the first exam. Of course, that doesn't mean it's not important. It just means you won't see it until a much later exam. The other thing that I want to point out is that the timing of this is not great, but it should be one of the last disruptions of the semester on Tuesday of next week, which is the 18th. I won't be available for in-person office hours. You're still welcome to contact me by email. Could probably set up virtual appointments those days during the exam, Monday, Tuesday, Wednesday, if we need to. But I have a conflict that comes up during the actual office hours period, so I won't be around for that. So apologize for that, but like I said, should not happen very much at all in the future. Okay, so we're going to get into continuing what we left off with last time, which is talking about VSEPR, which is a technique that we can use to take a Lewis structure and determine a three-dimensional shape of the molecule from that, and how all of the atoms that are bonded to the center atom and all the lone pairs are arranged. So what we're going to start with, if you recall last time, we talked about the situation when we have two electron groups around the center atom. That's where we have some combination of two atoms and lone pairs, three electron groups, and four. Took us up to the end of last time, which was the tetrahedral electron group arrangement. Today we're going to do 5 electron groups, and this is the one that's probably the most confusing, I would say. So it's the one that people often have a little bit of trouble with for whatever reason. So we'll make sure we spend enough time on it. I'm going to try to use that simulator again and see if Chrome is a little bit better behaved and doesn't bog us down like we got bogged down last time. So if we want to do 5 electron groups, if we're just going to start by adding 5 total atoms, and we'll do lone pairs a little bit later, we'll just add 3 more. All right, so this geometry here, you got to rotate it in the right way, is called trigonal bipyramidal. So if you look down in this direction, you can see that 3 of the atoms make up a perfect triangle. So that would kind of look like we had for trigonal planar when there's only 3 total. But then the other 2 are sticking up above and below that, kind of like flagpoles going right through that triangle. So that's the top and bottom. You have one in what are called the axial positions. So you have a triangle, and then you have one coming up, one going down. So what we call that is trigonal bipyramidal. So let's see if my tablet is normal speed. So the way there's a couple ways you can draw this. All right, so far so good. So we're gonna draw it from the side. So the triangle from the side is gonna look like this. And that's again saying that this one here that's shaded is coming out towards you. This one's going away from you. So this is our triangle. And then you have one above and below that make it trigonal bipyramidal. Another way that you'll sometimes see this drawn, or sometimes at least it's easier to appreciate, is actually draw the triangle out like this. So draw it like that. You didn't do a great job. Hang on. Not used to drawing it this way. So you attempt to draw an equilateral triangle better than I did, hopefully, but then you can show that there's one coming up above and below the triangle. So again, it's a triangle with one above, one below, and we call it trigonal bipyramidal. Now, the reason that this arrangement is a little bit more confusing than the rest, I wouldn't say it's terrible, but the reason it's a little bit different than the rest is because in the first 3 that we've done so far, you just had one bond angle to worry about. So linear was 180, trigonal planar was 120, tetrahedral was 109.5. All the atoms were equally far apart from each other in terms of their angles and their distances. In trigonal bipyramidal, you actually have 2 bond angles to worry about. So in trigonal bipyramidal, what you have are these angles here from one of the top or bottom atoms to the side is 90 degrees. So you have 90-degree bond angle there. But then in the triangle, just like we had last time for trigonal planar, you also have 120-degree angles in the triangle. So the angles that are in the plane are 120. And then you have the ones that are above and below that, which would have 90-degree angles to the ones nearest to them. So you have 2 different bond angles here, which means you have really 2 sets of inequivalent positions. You have the 3 positions that are on the triangle, and then the one above and below are a second set that are inequivalent from those other three. So that makes things a little bit different here. So then when you're going and starting to put lone pairs in, so if you have no lone pairs, if it's just 5 atoms bonded to the central atom, then the electron group arrangement will be trigonal bipyramidal and the molecular geometry. One feature of the simulator that I didn't even know existed until I saw it today, you can actually give the names and the geometries from that. And what you can see, they call it electron geometry, we call it electron group arrangement. So those are a little bit different terminology, but you can see they're both trigonal bipyramidal in the situation when you have no lone pairs on the central atom, as would be the case for any of them. In that case, the electron group arrangement and the geometry are the same. Now, if we want to take off one of the atoms and add an electron pair, non-bonding pair to the central atom, here again, we have a choice of where it goes. In the other geometry, it doesn't really matter. You can put the lone pair wherever you want because all the positions are the same. But here we can either put it around the triangle part, the equatorial positions, or we can put it in one of the top or bottom positions. And it turns out that those aren't exactly identical. Now, we said before that lone pairs want to be as far away from everything else as possible. They're even more strongly repelling than the bonding pairs are. And it may not be totally intuitive why this is the case, but what you'll just have to remember or try to intuit in some way is that when you have a trigonal bipyramidal electron group arrangement, if you have lone pairs in the structure, whether it's 1, 2, or 3, those are the three possibilities we'll have, they're all going to go on those triangular positions. So you're never going to put a lone pair on the top or bottom position in trigonal bipyramidal. So we'll see that's what happens when we do this. If we take off an atom and put in a lone pair, it kind of rearranges itself a little bit, but you can see that that lone pair ends up, to get it just in the right orientation, ends up in one of those three triangular positions around the side. Top and bottom still have atoms there. Now, this is the geometry that most people, if I don't know if there's a rhyme or reason to this, but when I look at homework questions and exam questions, even when I teach this stuff much later on to advanced students, or at least review it for them, this is the one that always trips people up for some reason. So if you draw it like that, it's pretty straightforward to draw in that orientation. Oh, I don't want to open that. That's the wrong one. So it's pretty straightforward to draw this. What you have, again, is a trigonal bipyramidal arrangement. So you have a triangle and then one above and one below. And we said the lone pair goes on one of the triangular positions there. Now, the name of this geometry is not as intuitive, I would say, because in order to really appreciate why it's named the way it is, you have to take this thing and turn it over on its side. In this orientation, you can't really tell what it's supposed to look like or why we name it the way we do. So we're going to take this whole thing, rotate it 90 degrees, I guess counterclockwise, and then what the picture will look like in that orientation is this. So those are the ones that are coming above and below the triangle. Those are the two, and those are the three triangular positions. So it's AX4E is the way we would name it because there's 4 atoms and 1 lone pair, and the geometry for that is called seesaw. So hopefully in this orientation you can see why we call it seesaw. I'll go back to the simulator and hopefully make that even more obvious. So if we go here and turn this on its side, that's what seesaw looks like. And again, it can rock back and forth like that. That's why we call it seesaw. If you're familiar with the playground object called a seesaw, hopefully that makes sense to you. All right, so that's the seesaw geometry, but there's one lone pair there on the one of the equatorial positions. Why do I keep accidentally clicking the wrong one? All right, so then the angles in this case, again, when you have geometries that involve lone pairs, the angles are more or less going to derive from the parent geometry, but then they're going to get compressed a little bit because of the lone pair. So if we look at these lone pairs here in seesaw, they're going to push down on all the atoms in the opposite side. So you're going to have this angle is a little bit less than 90. This angle here, which was exactly 120 degrees before, will be a little bit less than that. Not easy to predict how much less, but you would expect some compression of those angles because the lone pair is more strongly repelling, so it's going to push on everything and kind of compress it on the other side. So there's a little bit of a compression in bond angles whenever you have lone pairs involved. That's typically the case. All right, with 5 electron groups, then we have 2 other possibilities, which is going to involve putting either 2 or 3 lone pairs on the central atom. And I forgot the notes for this, so I'm going to have to wing it. So for AX3E2, though, we have, again, the pattern you just want to remember is that whenever there's lone pairs in this arrangement, when you have 5 total electron groups and one or more of them is a lone pair, the lone pairs always go on that triangular part of the shape. So we start with that basic shape here. All right, so again, if you look at, always just first look at the total number of electron groups. That's going to tell you the arrangement that they have, and then you fill in whichever ones are lone pairs after that. So with 5 electron groups, you're always going to start with the trigonal bipyramid. As we said, the lone pairs are always going to go on one of these 3 triangular positions. Here we have 2 of them. It doesn't matter which 2 because all 3 of them are equally far apart from each other. So to make the picture easier to see, I'm going to put them right here and here. That leaves X's there, there, and there. Let's see if that matches what the simulator tells us. Could have done that first. So if we go here and we take off one more atom and add another lone pair, what you'll see is, again, looking down, right orientation, gotta get it just right. We can see it ends up on one of the other triangular positions. And then if we orient it the way that I did on the slide over there, it's going to look like that. And we call this, it's sort of sideways, but we call it T-shaped. So there's, hopefully that one's fairly obvious. If you want to really see it, do it like that. But we call this the T-shaped geometry. So 2 of the 3 triangular positions are occupied with lone pairs. That leaves the other 3 atoms making this sort of T-shaped arrangement. Okay. So it's sideways in this direction, but hopefully that's not too hard to see why. And we call this the T-shaped geometry. In this one, we no longer have the 120-degree bond angles anymore because we've gotten rid of 2 of those 3 triangular positions. So what we have is only 1 bond angle now, which is going to be a little bit less than 90 degrees because of the effect of the lone pairs. I guess you could have this larger bond angle too, that's 180, around 180, but we typically just quote the smallest bond angles that are present, more so than all of them. So the smallest bond angle in this would be 90 degrees. Or just a little bit less than that. Okay, so that's T-shaped. And then finally, the last geometry that involves 5 electron groups is going to be AX2E3. In this case, all 3 of the triangular positions are occupied by lone pairs. This is not a very common arrangement, but there are some molecules that would fit into this. And we put all 3 of those positions with lone pairs, X above, X below. That one's not too hard to visualize. So remember, if we only have 3 atoms in the formula, it's either linear or bent. Those are the only options. This one is one of the ones that would end up being linear. Because what you have are 3 lone pairs pushing up equally in all directions. So they're going to keep the 2x atoms exactly 180 degrees apart. So if we go to the 3-dimensional structure here, you can see that it's a linear geometry. And again, looking down the top, all 3 of the lone pairs arrange themselves around the triangle. Okay, so that's the other one that ends up being linear. We had AX2 was linear. Now we have AX2E3 is linear again because the 3 lone pairs are all in those equatorial positions, and they don't compress the bond angles at all because you're getting basically the 3 lone pairs pushing up equally in all directions. So that effect sort of cancels out, and you don't have any compression of the bond angle. So the bond angle here, which would be just this one angle, XA and X, I'll write it out to make sure you're aware. This is exactly 180 degrees. So even though we have lone pairs here, there's no bond angle compression because they're pushing up and down with the same force basically, and so that keeps those 2 exactly 180 degrees apart. All right, so those are the situations that involve 5 electron groups. Like I said, that's the slightly more complicated one, in part because there's 2 non-equivalent positions, as we talked about, and because there's 4 possibilities, AX5, AX4E, AX3E2, AX2E3, all 4 possibilities that would have 5 total electron groups. All of them can exist in real molecules, so we have to be familiar with those. All right, so any questions on that? All right, the last one we're going to do, the highest we need to go, is to 6 electron groups. This one I think is not as bad. Let's look at it in 3 dimensions first. So what you have for 6 electron groups, the name of the geometry is not like super obvious, I suppose, but the shape is pretty easy to understand. So we're going to put 3, 4, 5, 6. That's as high as it lets you go in the simulator too. So even if you're using this, you can't even imagine what 7 will look like. There's not many examples of that anyway. So what this is called, and maybe the easier way to see it is, again, it's if you look down the axis, it's a square with 4 atoms, and then one above and one below the square coming straight out of the plane. Okay. Now we don't. You might be tempted to call this square bipyramidal. That's what we call it. We had trigonal bipyramidal for the last one. This one could be called square bipyramidal. That wouldn't be necessarily wrong, but the way that we name it in chemistry is called, drum roll please, octahedral. So it's not super obvious why we call it octahedral. I might have a, no, I don't have a picture of the notes, but if you imagine drawing triangles through each of these contiguous sets of 3 atoms all the way around, you get 4 on the top, 4 on the bottom. So there'd be 8 sides. So hedra is I believe is the Greek word for side. So if it's octahedral, that means there's 8 sides. So there's only 6 atoms around the center, but when you draw the 3-dimensional shape that encompasses those, that would be 8 sides. That's why I call it octahedral. So that's the electron group arrangement, and in the case of no lone pairs, that would also be the molecular geometry. Okay, so the way we can draw that, again, there's sort of 2 ways to draw it. One would be with the sort of wedges and dashes that indicate that you have a square with 2 of the atoms in the front coming towards you, 2 of the atoms in the back going away from you, one straight above that, one straight below that. Or the other way to draw it is to actually draw a square with one above and one below. All right. So it's perfectly fine to visualize it as a square bipyramid, because that's really what it is. But what we call it, as I said, is octahedral. And in this case, the bond angles are exactly 90 degrees. So around the square, you have 90-degree angles as you would in any square. And then from the plane up to one of the ones above it would also be 90. So 90-degree bond angles all around. So this is another one then where the positions around the octahedron are all equivalent. So when we start putting lone pairs in, it doesn't really matter where the lone pair goes because all those 6 positions are identical to each other. So if we go and do that then in the simulator, let's look at the situation where there's now a lone pair involved. So we take out an atom, we add a lone pair. What we'll see is that it doesn't really matter which of those 6 positions the lone pair goes in. This orientation is how I'm going to draw it, and it's kind of the easiest way to sort of understand the structure. So what we have here is a square base with one above it, so we call it square pyramidal. Again, looking down the top, there's a square base, and then you just have one atom coming out. So instead of being bipyramidal, it's just pyramidal. So in that case, we do use that nomenclature, but it's going to be square pyramidal. In this case, that's what's showing there at the bottom. Okay, so the electron group arrangement is still octahedral because there's still 6 total electron groups, including the lone pair. But the geometry, which only accounts for the positions of the atoms and not the lone pair, would be square pyramidal when you have that situation. All right, so the way we can draw that, if you like this, I don't know which of these forms you like better, but if we draw it as a square to sort of emphasize that, doesn't matter which of those 6 positions have the lone pair, but it makes it most obvious what the geometry is called if we put it at the bottom. That's not behind. There's the is behind. That's probably better to do it. All right, but anyway, that's what we get. So a square base with one capping atom, so we call it square pyramidal. This lone pair does sort of push up the square base a little bit, so it's not, even though a simulator doesn't quite indicate that, it's not totally flat. These kind of get pushed up a little bit. So these angles here would be a little bit less than 90 degrees because of that. So it's kind of like taking an umbrella and like partially folding it up. So the bond angles are a little bit less than 90, at least the ones that involve that apical position. But that it would still be close to 90 because it comes from the octahedral arrangement. All right. And then the very last one that we have, so with 6 electron groups, you're only going to have either 0, 1, or 2 lone pairs. So with 2 lone pairs, we're going to have this one here. Now, in this case, though, we can't just willy-nilly place the lone pairs wherever we want. So when we have the 6 electron groups, we're going to get the octahedral arrangement. But then we have to decide where the 2 lone pairs go. Doesn't matter where the first one goes. For all 6 of those positions are equivalent. But if we put the first one at the bottom like we did before, remember that lone pairs repel more strongly than bonding pairs. So if we have 2 lone pairs and there's a chance to get them even further away from each other, that's what we want to do. So if the first lone pair is down here, the one that where you want to put the second one to minimize the repulsion is all the way at the top, 180 degrees from the first. So this is the one situation too, where if you have similar to with 5 electron groups, but even in this case, it only appears here. With 6 electron groups and 2 lone pairs, you want the lone pairs to be 180 degrees apart from each other. It could be any of the pairs of positions that are 180 degrees apart. If we do it like this, then you can hopefully see what the geometry is called. And then another way to draw this, so if we go back to the simulator, take off an atom, put one lone pair on, this is sort of how I drew it there, with 2 atoms coming towards you, 2 away from you, lone pair above and below. If we look down, you could an easier way to draw it and visualize it is like that, where it's just a square of 4 atoms. So in this case, the 4 atoms make up a square. You can draw it sort of in the plane of the page is easier. In this orientation, you can't really easily show the lone pairs, but there would be one coming out of the board straight at you, that, and one going back away from you. So lone pairs would be implied in this case. They're still there. They're not missing. But in this orientation, you can't really easily draw them because they're exactly perpendicular to the page in terms of orientation. But it makes it easy to see what we call this geometry, which is square planar. And we have exactly 90-degree bond angles. I had a rather old and curmudgeon-y professor in graduate school who used to always say, why do we call it square planar? Like when is it, we should just call it square because a square is always a plane. But that Web of Science is pretty particular with how you format your answers. So always call it square planar. If you just write square, while not technically incorrect, that's just not the way that we call it in chemistry, again, for reasons that are beyond my control. The square planar is the proper geometry for that. And that's the last one we have to worry about. All right, so that's going to take us to the end of just pure VSEPR theory. So what I included here, also before we get into the final summary, is just a little bit more about some situations where the bond angles could be compressed from their ideal value. So we said that lone pairs will always do that. We saw in most of the examples that have lone pairs, with the exception of AX2, E3, where the 3 lone pairs are pushing equally, and then same story for AX4, E2. But in most cases with lone pairs, you do get compressions of the bond angles. So we have the ideal values that come from the electron group arrangement, and those you'll sort of need to internalize: 180 degrees for linear, 120 for trigonal planar, 109.5 for tetrahedral, 90 and 120 for trigonal bipyramidal, 90 for octahedral. So you have those ideal angles that come from the shapes, but then sometimes you're going to get slightly smaller values than that. Lone pairs is the one we've already talked about that does that. The other thing that sort of does this, it's not a huge effect, and it's not one we're going to encounter a lot, but would be if you have double bonds or triple bonds in the structure, especially if they're not all the same, but if you have one bond that's a multiple bond with one or more other bonds that aren't. So as an example of this, the prediction we would make is that if we have this molecule here, which is called formaldehyde, if you've heard of that. So that molecule here, we have an AX3 structure. The carbon has 3 atoms around it, no lone pairs. So it's AX3. We would predict that it's trigonal planar. So in a perfect world, those bond angles would be exactly 120 degrees. But the prediction we would make is that when we have a double bond there, now you have a bond that has 4 electrons, opposing bonds that only have 2. So that bond with 4 electrons is going to push down a little bit stronger because it has more electron density in it. So that's going to sort of push these bonds down like this, and that's going to make this angle down here between the 2 hydrogen atoms a little bit less than 120 degrees. That would make these ones a little bit bigger then. The whole thing is still planar, but so if you make one angle smaller, you're going to make the other 2 bigger to accommodate that. We're going to get a little bit of a distortion of the bond angle because of that double bond having more electron density. pushes down a little bit harder. That's at least a prediction you would make. That doesn't always happen because there's other factors that are more subtle, but that's a common thing you'll see. But the important thing to keep in mind is that when we're deciding, where to put lone pairs and the effect that they might have on the bond angles, always remember that the repulsion between two lone pairs. So if you have two lone pairs in the structure, that repulsion is the strongest. So that's going to be the one that, again, is going to dictate where those lone pairs go in some situations. You want them as far away from each other as possible. And it's also going to have an effect on the geometry more than a double bond or triple bond would. Those lone pairs are much stronger in that sense. All right, so let me close this so it's in case it starts slowing us down. All right, so now we're going to just go through a bunch of examples, and some of these would be good because it starts with a Lewis structure, and Lewis structures is going to be covered in the first exam. So we'll get to review that a little bit. I won't go through like all the nitty-gritty details on every single one, but at least for the first one or two or some of the weird ones, I'll go through the Lewis structure. So if we want to determine the molecular shape of PCl3, that's this question asked. Again, that's going to require us to at least draw a Lewis structure that has the correct number of lone pairs on the central atom. We don't really care about double bonds, triple bonds as much in the case of VSEPR. That's not our primary concern, but we have to have the right number of electron groups around the central atom. Now we know there's going to be 3 atoms because the formula is PCl3. So it's going to be AX3 something, but to get the geometry correct, we have to determine how many lone pairs there also are because that's going to dictate what the arrangement of all those electron pairs would be. So that starts with a Lewis structure. So let's review how to do that since I wasn't here today that you actually did cover this. So we have phosphorus and chlorine in this molecule. So we have to first count up the number of valence electrons that we have available. And that's going to come from the periodic table. So we have PCl3. Phosphorus is in group 5A, so that's going to bring 5 valence electrons, S2 and P3. And then chlorine is in group 7, 2 over from that, so each chlorine is going to bring 7 valence electrons. So when you're drawing a Lewis structure, there's really, unless you're just really good at doing these things in your head, you really need to look at the periodic table first and make sure that you're counting the correct number of valence electrons for the whole structure. So PCl3 is going to have 5 electrons, valence electrons from each phosphorus, 7 valence electrons from each chlorine. We just have to add all those up together to figure out the total. So one phosphorus has 5 valence electrons. 3 chlorines each have 7. There's going to be a total of 26 valence electrons in PCl3. No charge, so we don't have to add or subtract any from that. All right, so then we draw the Lewis structure for PCl3. We start with the central atom. We begin with single bonds to all the outer atoms. So we always start with that for a Lewis structure. Central atom, single bonds to the outer ones. And then the first thing that we always want to do is complete the octet of the outer atoms. There will be rare situations when your central atom has an incomplete octet. There will be other situations where the central atom has more than 8 electrons, but your outer atoms, that you're never really going to see exceptions there, unless they're hydrogen. So remember, hydrogen just gets a single bond and you're done. Please don't put lone pairs on hydrogen. I would, small piece of me dies whenever I see that, so don't do that. But for any other outer atom that's in the P block, nitrogen, oxygen, fluorine, chlorine, all the halogens, you're going to want to complete their octets with lone pairs. So we have 1 bonds when you have 3 lone pairs to add 6 more electrons. So now we have a complete octet because there's 2 electrons from the bond, 6 more is lone pairs. Do that for all 3 of them. Then we're going to take stock of where we are in our electron count. So we've completed 3 octets. You have to be a little bit good at math to do this, but not too good. So 3 times 8 is 24. We have 26 available to us. So that means we have 2 more to go. And so with those extra electrons, whatever we have left, those are the ones that go on the central atom as lone pairs. So that's going to be our last 2 electrons that we put in. As I said, we don't have to worry about whether there's double bonds or triple bonds. In this case, there aren't because we already have all of the octets complete. And if we were to calculate formal charges for all the atoms, they're all 0. I'm not going to do that right now. For VSEPR, again, you don't have to worry about things like formal charges and all that. You just have to get the number of electron groups correct. So what we've determined from this is that this is AX3E. We already said the X3 comes from the formula. We have 1 lone pair, so that makes it AX3E. 4 total electron groups means that they're going to arrange themselves in a tetrahedral arrangement, which looks like this. And it doesn't matter where the lone pair goes. I like to put it at top to make it easier to see. And what we call that is trigonal pyramidal. So in this structure here, the 3 chlorines make a triangular base, and then the central atom phosphorus is sort of above that triangle, making a trigonal pyramid. All right, so lone pair is still there, but the molecular shape or the molecular geometry only accounts for the atoms. All right, so any questions on that? All right, let's just do some more examples. Let's do it for the carbonate anion, CO3 2-. So we can use VSEPR on anions as well. So not just on cations. So if we have CO3 2-, we have to again count electrons for this. So this one has carbon and oxygen in the formula, so we have to get their valence electrons first from the periodic table. Carbon is group 4, 4 valence electrons. Oxygen is group 6, each one has 6. So that just comes straight from the group number when you're talking about main group elements. 4 and 6 for carbon and oxygen are the number of valence electrons. So CO3 2- has 1 carbon. Oxygen, there's 3 of them in the formula, each bringing 6. Now, what we have to be a little bit careful about here, though, is whenever we're dealing with ions, you have to either add or subtract additional electrons depending on the charge. So this one has a 2- charge, which tells us that we're going to have 2 extra electrons in our total count. So our total in this case should be 24 electrons. 22 of those come from the atoms, the extra 2 are because of the 2- charge. Now, once we get to that electron, once we get through the electron counting part, drawing the Lewis structure of any of the ions that we would have, any of the polyatomic ions that we've already learned about, those are going to proceed exactly the same way once we get the number of electrons correct. So for CO3 2-, start with single bonds to all the outer atoms. Complete their octets, so add 6 more to each of those to get to a total of 8, 2 from the bond, 6 from the lone pairs. And then we take stock of where we are. We've completed 3 octets, but that's all 24 of our electrons. So we don't have any more lone pairs for the central atom because 24 electrons is the total that we have. We've used all 24 to complete the octets of the outer atoms. However, this one does have a small problem, which is that the carbon right now only has 6 valence electrons around it. And unless it was boron, you wouldn't want to stop at 6. You want to make sure that your central atom has at least 8, exactly 8 if it's carbon, nitrogen, or oxygen. So we want 8 valence electrons. The way that we have to do that is draw a double bond. Now we can't just slap a double bond in, that'll add extra electrons. We have to take off one of the lone pairs from oxygen and make it a double bond. And this whole thing would be 2- charge. That's a little bracket there. Now, as you might recognize, technically speaking, there's going to be 3 resonance structures for this because we can put the double bond in any of those 3 positions, and that would be equivalent. So we could draw the other 2, but we don't really care about that for VSEPR. VSEPR, we really don't even need to include the double bond at all. Whether you have the double bond there or not, or whichever resonance structure you ended up drawing, or drawing all 3 of them, however much detail you got to, you would find that this has an AX3 structure. Or sometimes it would be called AX3E0 to indicate that there's 0 lone pairs on the central atom. So you can tell from the formula that there's 3 atoms around carbon, 3 oxygens. By going through the Lewis structure, at least most of the way through, we find that there's no lone pairs on the central atoms. That makes it just AX3 by itself. No E in that formula. So AX3 is just going to be a trigonal planar electron group arrangement, and the molecular geometry then would also be trigonal planar because there's no lone pairs. All right, so whenever you have a structure that has 0 lone pairs in the central atom, the electron group arrangement and the molecular geometry have the same name and are the same. All right, questions on that one? All right, the last one we have is, I think it's the last one. Yeah, a little bit of an oddball, but it does exist. So we haven't talked about it a lot, but you've probably heard the dogma that, the noble gases, they're called noble because they don't react with anything. And generally speaking, that's true. But there are some rare examples of noble gas compounds, and with xenon Xe, you can make compounds with fluorine. So you have xenon difluoride, which is XeF2. This one is xenon tetrafluoride, XeF4. Both of them exist. You wouldn't want to like snack on them or anything. They're pretty reactive, pretty nasty things, but they do exist. And we can draw their Lewis structures using what we've learned so far in this course. So if we want to get the Lewis structure for this and then predict the geometry, the molecular shape, we have xenon and fluorine in the formula. Again, even though it's not common, when we have compounds of noble gases, they're in group 8, so they do bring 8 valence electrons for us to use. So we have 8 valence electrons for xenon. Fluorine is way up here, but it's just one column over, so it's group 7, and that's going to be 7 valence electrons for each fluorine. Your goal, maybe you won't get there, but it's something to aspire for, is to practice enough Lewis structures that you don't even have to look at the periodic table to get the number of valence electrons in most cases. But anyway, we always have the periodic table available, so you don't have to get to that level, but you probably will, even if you don't try to. So with xenon, we have 8 valence electrons. Each fluorine, there's 4 of them, brings 7. Now, one pattern you'll start to see is that if the number of valence electrons is not a multiple of 8, that means that you're going to have lone pairs in the center atom. You have to figure out how many lone pairs there are, and I guess if you're good at math, you could probably predict there's going to be 2, because we have 4 octets, that leaves 4 more electrons, 2 pairs. But it's still good to go through the whole process of drawing the Lewis structure, which you will have to do anyway on exams, and make sure you don't make any mistakes there. So for xenon tetrafluoride, we start with single bonds to all the outer atoms. And again, initially, we don't really try to make any sort of realistic geometry because we don't know what it is yet. We just arrange them around in any random way. Single bonds to each of the outer atoms. Complete the octets. All right, and so then what we would have is, as I kind of already hinted at earlier, we've completed 4 octets. 4 times 8 is 32. We have 36 electrons available to us, so we have 4 more to use. So that means we put 2 pairs on the central atom. All right, so in terms of VSEPR, that's as far as we need to go. If you're drawing a Lewis structure, you'd always want to possibly evaluate whether you need double bonds or not. We don't need double bonds here. Our central atom is already beyond an octet, and fluorine will never have double bonds anyway, because that would put a positive formal charge on it, and fluorine is super electronegative, so it doesn't want to have positive charges associated with it. So we just have this structure here is the final structure, and then in terms of the AXE nomenclature, there's 4 atoms, and then now we have 2 lone pairs, AX4E2. So this was the very last geometry that we covered, which is an octahedral arrangement. And then we end up putting the 2 lone pairs as far apart from each other as possible, like that, leaving the 4 atoms in a square, or more precisely, square planar geometry. Okay. So, as I said, Lewis structures become important in this chapter because you need to be able to do that to be able to predict the geometry, as well as some of the things about bonding that we're going to cover in the next class. All right. So any questions on VSEPR? That's taking us really to the end of that specific part of the discussion. Yeah. Well, so for a Lewis structure, there really is no attempt to indicate the real shape. The Lewis structure is two-dimensional. There's not really a specific shape. Now, when you're getting into taking that Lewis structure and then, so this Lewis structure, there's really no, I mean, I drew it square planar because I had 4 things to put around the center atoms. I put them in a square because that's what I'm in the habit of doing. But before, you wouldn't know what the shape is until you had the Lewis structure. Now, when you're drawing the shape, this one here is kind of showing it with the square kind of like coming out towards you, or maybe tilted a little bit. You can draw it however you want. I mean, I think for problems, you have to look at how the homework assignment is formatted. For problems that involve shapes, you're going to likely just be selecting an answer or naming it, not necessarily drawing it. So for Lewis structures, there shouldn't really be any concern about how the atoms are arranged or what shape they're in. It's totally random for a Lewis structure, and not any attempt to indicate what the shape really is. So that's kind of the difference. In chapter 3, when we're talking about Lewis structures, we're just trying to show how the valence electrons are arranged. How are they bonded between the central atom and the outer atoms? Are they single bonds, double bonds, or some combination? Where do the lone pairs go? But the shape is not, you're not really trying to indicate that. When you go to VSEPR, there's different ways of drawing the shapes, and I've tried to indicate in some cases multiple sort of depictions of that. But however, whatever orientation you choose to draw it in, it's kind of up to you, and it's really just a matter of how you best visualize it. So another way to draw this one, as we talked about, would be like this, just as a flat square. Although with the understanding, not easy to really explicitly show that you still have the two lone pairs there, but one of them is coming straight towards you, one of them away from you. But the four atoms, which is what you care about for the shape, are in a perfectly flat square arrangement. Okay, any other questions? All right, so what I have here to hopefully help you, again, I discourage memorization, but here's a sort of table that summarizes all the different possibilities that we covered. So there's 5 electron group arrangements, steric number of 2, 3, 4, 5, or 6. That's the number of electron groups around the center atom. And when you have no lone pairs, then the electron group arrangement and the geometry have the same name. You start adding lone pairs and you get all these different possibilities. So that covers the entirety of VSEPR as it applies to this course. Again, I think the best way to learn it, though, is to really try to visualize the shapes and start with the electron group arrangement, add the lone pairs in, and then sort of see what's in front of you rather than trying to just brute force memorize that AX3E is trigonal pyramidal, for example. But however you choose to learn it is up to you. This will hopefully help you as you're getting going on that. All right, what we're going to move into today then for the rest of the time is one of the things that we can predict from VSCPR is the polarity. I gotta give me like 1 second to check something. Um, well, my daughter's sick today and I can't check the message right now, so hopefully she's fine. All right, so what we have, she's in good hands, so I'm not just blowing her off for chemistry, don't worry. But I can't check the message right now. It's an app that's blocked by UH, believe it or not. So anyway, for what we're going to talk about the rest of the day, one of the things that we can predict um, from VSCPR, what's the point of having the three-dimensional shape other than just knowing what it is? We can predict some properties, and the first one we're going to talk about is polarity, whether a molecule is polar or nonpolar, meaning are the electrons sort of arranged equally around the central atom, or is there some asymmetric arrangement, some region where there's more electron density, less electron density? So where this kind of starts and is somewhat related to our polar bonds, which we covered back in chapter 3 not too long ago. So if you have just two atoms bonded to each other, we talked about the idea that if their electronegativity values are different, there's going to be some polarization of that bond. So the electrons are shared, but they're not going to be shared equally. So we talked about how in that case, the electron density is going to be skewed towards the more electronegative atom. Classic example is HF, which if we draw the full Lewis structure would have lone pairs on fluorine as well. But for the purposes of polarity, all we would need to know is that fluorine is the most electronegative atom on the periodic table, significantly more electronegative than hydrogen. So we would have an asymmetric distribution of the electron density towards fluorine. So we would have those are sort of two ways of indicating it, delta plus or delta minus. Um, sorry, I think there's one thing I need to check this. I'm sorry, because I just have to do one more thing. Really annoying that UH blocks things now. getting it. All right. Sorry about that. Um, well, that's how we would do it. When we're talking about the polarity of a bond, if we say, is this bond polar or not polar? Is it more polar or less polar? Again, it's just considering the two atoms that are bonded to each other and what their difference in electronegativity is. That's all that we care about. And then we can compare how polar it is. Is it more or less polar? Which that's going to be determined by the difference in electronegativity, which we often abbreviate as delta En. The not really change in this case, but the difference in electronegativity between the two atoms. So if we have carbon bonded to all of the halogens, the bond polarity is going to decrease as we move down the series because the electronegativity of the halogens decreases. So we have carbon bonded to all of them. This one's going to be the most polar because there's the biggest difference in electronegativity between carbon and fluorine. Carbon is sort of middle of the road in terms of electronegativity. It's not super electronegative. So fluorine is more electronegative. You have a pretty big difference there. Carbon and chlorine are closer together in electronegativity, but still polarized in this way. Carbon and bromine, less polar still because bromine is less electronegative, so that gap is closing. And then carbon and iodine have nominally the same electronegativity values, so it's not perfectly nonpolar because they're two different atoms, but to at least to the precision of the scale that we have, it's basically a nonpolar bond because the two atoms. So that was some stuff we talked about in chapter 3. If we're asking you how polar the bond is, it comes from the difference in electronegativity. The biggest difference means that it's more electronegative. But what we're or more polar. So what we're getting towards today, though, is the idea that we can also predict the polarity of an entire molecule. So if we just have a simple diatomic molecule like HF, then difference in electronegativity is all we need, predicting whether it's polar or not, or how polar it is. But if we're talking about these more complicated structures that have 3 or more atoms in them, how do we rationalize whether that whole molecule is polar or not? We can talk about it for the individual bonds, but what we also want to care about is whether the entire bond itself is polar and the entire molecule itself is polar. So for molecular polarity, we're talking about the idea that sometimes over the entire more complicated structure of a molecule, you'll have an uneven distribution of charge. So it's an uneven distribution of charge over a whole molecule. I'm going to put here or a large portion of it. This is not really a situation we're going to encounter in this course, but if you have complicated biomolecules, for example, like you probably heard of lipids, fatty acids. Sometimes what you'll have in those is like a part of the molecule that's non-polar and a part that is polar. So like the whole thing is not necessarily polar, but a good part of that molecule will be polar. So it's an uneven distribution of charge over the molecule or some portion of it. Now we're not going to really talk about this in quantitative sense in this course. We're not going to be measuring or doing calculations about polarity, but there is a way to sort of measure it and quantify it that I just want to briefly introduce to you. So the unit for polarity is called the debye, abbreviated as capital D. And it's equal to, I'm not sure exactly where this number comes from, but it's 3.34 times 10 to the minus 30 coulomb meters. So this unit here is the unit of charge, coulombs. And the whole idea that this is telling us is that just from the units alone, you can tell that when you're talking about a dipole, it's how polar something is a function of the charge that's involved, how much charge imbalance is there, as well as the distance over which that occurs. Again, don't really worry about this too much. I just wanted to make sure you're aware of it. And the way that we quantify this is called the dipole moment. So if you wanted to actually quantify how polar something is, you would do that via the dipole moment, which is abbreviated as mu, which I can't write very well, but all right. So mu is the dipole moment, and all right. So that's how we would sort of measure and quantify it. So to predict molecular polarity, then there's sort of two criteria that need to be true. One is that the molecule must have polar bonds. If the molecule's bonds are all nonpolar, then typically the molecule itself will have to be nonpolar also. So if you're talking, so there's some molecules that are very easy to predict their polarity, what are called homoatomic molecules. Those are going to be molecules that they have more than one atom in the structure, but the same type across the whole structure. So a lot of diatomics like N2. As we'll learn later on in the course, some of the elements exist in more complicated structures like P4. So the standard form of phosphorus is 4 atoms of phosphorus bonded together. That molecule would have to be nonpolar because all the bonds are nonpolar. Same with S8. When the same atom is bonded to itself, the bond is nonpolar. And then if you have a more complicated structure with that, the whole molecule would also be nonpolar. So those are typically the easy ones for us to predict. So these ones, I'm going to put a little asterisk here because there is one exception to this. A molecule you've probably heard of, which is ozone. I'm not going to go through it in detail today, but if it shows up for you, if you draw the Lewis structure of ozone, you actually have formal charges in the molecule that you can't get rid of. So whenever you have formal charges, that would indicate that there is some sort of polarity because you have, again, a positive charge and negative charge in different parts of the molecule, indicating that the charges are not equally balanced. So that's an example where it's just 3 oxygen atoms, so you would not easily predict that it's polar because it's the same atom bonded to itself, but it ends up being that way. But for anything else that you see, that this would be like really the only one exception that I can even easily think of. So anything else like N2, H2, Cl2, P4, S8, whatever the case is, those would easily be predicted to be nonpolar. But even in the situation where the molecule has polar bonds, so if you say, okay, well, the molecule does have polar bonds, let's say it's like CF4, carbon with 4 fluorines. We know that carbon and fluorine have different electronegativity values. Okay, those bonds are polar, but that alone does not tell you that the whole molecule is polar. So what you also have to think about then is the geometry. So the presence of polar bonds does not guarantee that the molecule itself will be polar. And that's because depending on the arrangement of those bonds around the central atom, you may or may not cancel out those individual bond dipoles. And so that's where we have to think about the three-dimensional geometry and whether do those individual polar bonds, the dipoles that each of them have, do they cancel each other out or not? And that's going to determine then whether or not the molecule itself is polar. So this is sometimes a topic that's a little bit annoying to deal with, but there are, as I'll give you a table at the end that kind of expands the VSEPR table that I just showed you that makes things, I think, a little bit simpler. But the first one that is an easy one for us to remember is that if you have no lone pairs on the center atom and all of the X's are the same, so there's only one type of outer atom, in that case, the molecule will always be nonpolar. So for AX2, AX3, AX4, AX5, AX6, with no lone pairs on the center atom, all of those are going to give you nonpolar molecules as long as you only have one type of X outer atom. Okay. So this, again, just to reiterate that, this only applies when all of the X's, the outer atoms, are the same. So all of these different structures are nonpolar. Perhaps the easiest one to visualize would be AX2. So if we have carbon dioxide, that's going to be in the AX2 arrangement with a linear geometry, 2 lone pairs on each oxygen, not that we care about those so much. Each of the carbon-oxygen bonds is polar, so carbon and oxygen have pretty different electronegativity values. Oxygen is to the right of carbon. Oxygen is the second most electronegative atom after fluorine, so it does have a significant polarity for each of the bonds, but they totally cancel each other out. Because you have a dipole going in this direction, but it's totally canceled out by the dipole going in the opposite direction. You can almost think of these dipoles like vectors if you're at all familiar with that. So you have one vector pulling this way, one vector pulling that way, and that there's no unbalance in that. Now, if you wanted to draw the sort of delta plus, delta minus, what you'd have is sort of delta minus over here. Yes, 2 delta plus on carbon because there's 2 polar bonds, but they all cancel each other out because they're evenly distributed in all directions. All right, so these are all nonpolar. It's sort of less obvious for the other ones. So like BF3 is an example, trigonal planar. In this case, the dipole vectors have both x and y components. So unless you're really good at that kind of math, it's hard to easily rationalize this. But again, still nonpolar. I'll write all these out. AX2 nonpolar, AX3 nonpolar. It's now in 2 dimensions, so not as easy to visualize, but these 3 vectors would all cancel each other out, and you have no net dipole in that molecule. And then any of the other ones too. So even for CF4, which is tetrahedral, AX4. Now we're in 3-dimensional space. Tetrahedral is sort of a weird geometry, so not intuitively obvious, but nonpolar because all those individual vectors, each CF bond is polar. So you have a dipole pointing towards each fluorine, but they all cancel each other out. So for any of the 5 basic geometries with no lone pairs on the center atom, you would predict nonpolar structures in the cases where all the outer atoms are the same. Now, if we go to another situation that we will sometimes encounter is structures with more than one type of outer atom. So you might call these like AX, X prime, EN structures where there's 2 different types of outer atoms. So it's not like CO2, which is two oxygens around carbon. As an example, what if we had COS? So if we had COS, you would predict a structure that's almost identical to CO2, still linear, but you replace one of the oxygens with sulfur in this case. It nominally would be AX2 because it's a center atom with 2 atoms around it, but really a better way to write this is AX, X prime. And so what you would have then is, for this situation, a pretty large dipole from carbon to oxygen, because oxygen has a much larger electronegativity than carbon. Sulfur is only a little bit more electronegative than carbon, so the dipole pointing in this direction would be much smaller, and so you would still have a net dipole moment pointing towards oxygen. In other words, there's 2 dipole moments in opposite directions, but they don't cancel each other out in this case because the polarity of the carbon-oxygen bond is much larger than the polarity of the carbon-sulfur bond. So if there's 2 different types of bonds, they typically don't perfectly cancel each other out, and so in this case, you would be polar even though it is an AX2 structure with no lone pairs. So then another example of this would be, there's a lot of molecules centered carbon that would have more than one type of outer atom. So if we had this molecule here, which is called chloroform, CHCl3, I'm not going to draw all the lone pairs in, but basically in this molecule here, the carbon-chlorine bonds are polar. CH bonds are not very polar at all, and the polarity points a little bit towards carbon. So again, in this situation, you don't have 4 equal and opposite dipoles that cancel each other out. You would have a net dipole that points towards those chlorine atoms at the bottom. Not so much concerned with the direction of the dipole in this course, but just really making the determination, is it polar or is it not polar? So this one would be polar. So the general situation, of course, there could be rare exceptions to this, but if you have structures with more than one type of outer atom, so for example, COS, CHCl3, where there's more than one different thing bonded to the center atom, those are going to be almost always polar. There still are, again, some rare examples of structures you could draw, mainly in the, AX, mainly the 5 or 6 electron groups. There are rare examples you could draw where the dipoles still cancel each other out, but for most common situations, you would just predict these are polar, and that's typically the level of prediction you'd have to make anyways, is whether it's polar or not. So when you're doing problems like this, especially these, I don't know, again, the homework questions could be a little bit different because we have a new system now, but if you have a test question that says, gives you a list of like 4 or 5 compounds and says which ones of these are polar or non-polar, try to find the easy ones first. And like I said, the easy ones are going to be ones that is all the same atom bonded to itself. H2, N2, O2, they're always nonpolar. And in this case here, if you have more than one type of outer atom, typically those always are polar. So you can usually quickly identify at least some of them. For the rest, you may have to go through a little bit more in-depth analysis. And so then if we think about the other possibilities then within VSEPR, there are some patterns that emerge. So if you have structures that have one lone pair on the central atom, so that would be AXME1, where there's one lone pair in the central atom, some number of outer atoms, whatever that is, these ones are always polar. So some examples of this are NH3, ammonia. If you draw the Lewis structure for ammonia, you would find that there's a lone pair in the central atom, which gives it a trigonal pyramidal structure. And because we've replaced one of the atoms with a lone pair, we don't have 4 equally opposing dipoles anymore. We have 3 that all sort of point in the same direction towards the nitrogen, and so they don't cancel each other out. But again, that level analysis is not usually required. You know that if it has one lone pair, it has to be polar. That's going to be true for any of these common structure types. One lone pair on the central atom gives you a polar structure. Another one would be SO2. So for SO2, the Lewis structure that minimizes formal charges does have 2 double bonds, but it leaves one lone pair on the central atom. And even though we have 2 equal SO bonds here, because the molecule is bent, they don't cancel each other out. So the 2 dipoles are not exactly opposite each other. They're pointing down a little bit, so they don't cancel each other out. So this one would be polar as well. Another useful thing to remember that's sort of related to this all bent molecules are polar. So we have a significant subclass of compounds that have 3 atoms in the formula, AX2 something. And in that case, the 2 possibilities are linear and bent. If it's linear, it's nonpolar. If it's bent, it's polar. So that's an easy distinction as well. Okay. And then the only ones that are then a little bit confusing. So if there's 0 lone pairs in the central atom, it's nonpolar. If there's 1 lone pair in the central atom, it is polar. The only ones that then require a little bit of extra thought and effort are the structures that have more than 1 lone pair, which there aren't too many possibilities. But the reality is that with more than 1 lone pair, E2 or E3, which is as high as we'll go, the unsatisfying answer here is that they may or may not be polar. So there's no easy rule here. So when we have water, which is H2O, it's AX2E2. This is another example, though, of a bent structure. As we said, all bent molecules are polar. So this one has 2 lone pairs, but it's polar because it's bent. Two dipoles point towards oxygen like that. And again, even though they're the same, they don't completely cancel each other out because they're sort of pointing up like this, meaning that there's a net dipole towards oxygen. So water is polar, has 2 lone pairs, but then there's another structure here that we covered earlier today, xenon tetrafluoride, which had 2 lone pairs. Which had this square planar structure, AX4E2, and we don't really care about lone pairs when we're doing polarity. So if we draw it in the more convenient orientation like this, what we would find is that we have dipoles towards fluorine, but they cancel out vertically and they cancel out horizontally. So kind of like in linear molecules, you have 2 dipoles that cancel out. Here we have that happening twice. Two dipoles that are vertical cancel out, 2 dipoles that are horizontal cancel out. So this one square planar would be nonpolar. All right, so with 2 or 3 lone pairs, again, there's not an easy rule to remember that it is or is not polar. Linear and bent is an easy distinction, but for some of the other ones, you have to think about it a little bit. But that said, those are only a sort of a minority of the cases, and so it's not something that's going to hopefully cause us too much trouble. And like I said, there's a summary table later on. So let's then do some predictions about polarity and go forward from there. All right, so if we have the first one here is PCl5. So PCl5 here, we want to indicate its shape and determine if it's polar or nonpolar. So for PCl5, we have to draw the Lewis structure first to get the idea to eventually get the geometry and determine its polarity. So phosphorus is, we did PCl3 earlier. This is PCl5, so just a different compound that has a different ratio. Phosphorus has 5 valence electrons in group 5. Each chlorine has 7. So the only difference here is that there's 5 chlorines in the structure instead of 3. All right, now again, 40 is a multiple of 8, so our easy prediction right off the bat is that there's no lone pairs in the central atom because we're going to complete our octets and not have any left for the central atom if that's the case typically. If we draw that out, what we end up with is, again, we don't really care about the shape initially when we're doing the Lewis structure. We just try to spread things out. Single bonds, complete the octets. And so then what we'll see is that for PCl5, we have 5 octets completed, 5 chlorines each with 8 electrons. That's all 40 of our electrons. And so this is going to be an AX5 structure, or AX5E0 if we want to indicate that there's no lone pairs. But because it's a structure that has no lone pairs on the central atom, we would predict that it is going to be trigonal bipyramidal. And nonpolar. All right, so no lone pairs on the central atom typically leads us to the prediction of it being nonpolar. All right, so if we just go through some other examples, IF3 is the one that we have here. Indicate if it's polar or nonpolar. All right, so this is what's called an inner halogen compound. It's a compound that's made up of 2 different halogen elements, iodine and fluorine. And we're going to take the same approach here. We're going to draw the Lewis structure, predict the shape, and then predict the polarity. So iodine and fluorine are both group 7 elements. So each of those in the structure is going to bring 7 valence electrons from different subshells, but still a total of 7 for each of them. So it's going to be iodine and fluorine, 1 iodine that brings 7 valence electrons, 3 fluorines that bring 7 each. So there should be 28 valence electrons in the structure. 28 is not a multiple of 8, so we're going to have lone pairs involved in the central atom. And so let's go ahead and draw it out. Then 3 fluorines, complete their octets with lone pairs. So you need to practice this enough to get relatively fast at it like I'm doing. So we start with single bonds and completing the octets of the fluorines. That is going to be 24 of our electrons used up. 3 octets is 24. We have 28, so that means we have 4 more or 2 pairs that go in the central atom. All right, so we get 2 lone pairs on the central atom, and then if we want to do it in terms of the AXE geometry, that's AX3E2 in this case. 3 atoms, 3 fluorines, and then 2 lone pairs is E2. So that's going to come from then a trigonal bipyramidal arrangement. We put lone pairs on the triangle, and that's going to leave this molecule being T-shaped. All right, so this one is T-shaped in terms of its molecular shape. Now, what is the polarity? Is it polar or nonpolar? That's usually the only determination we have to make. This is not one of the very obvious ones because with 2 lone pairs, as we said, it could be polar or it could be nonpolar. There's no easy rule there. But if we think about the dipoles in this case, these 2 more or less cancel each other out because they're opposite of each other. But we have another dipole pointing towards fluorine that is not opposed in the opposite direction. So this molecule would have a net dipole moment. There's 3 dipoles. They don't cancel each other out. 2 of them more or less do, but this third one here, the horizontal one that I've drawn, is gonna be there. So we have a net dipole left to right, making this molecule polar. So T-shaped is the geometry, polar is the polarity. All right, questions on that? All right, so then just to close this out, what we have here is what I hope is a fairly helpful table as well, that not only summarizes the VSEPR part, but also whether each of these structures is polar or nonpolar. And you don't want to just, again, blindly apply this knowledge, because remember, this only works if these are structures where all of the outer atoms are the same. If that's not the case, that usually makes it polar, but you have to think about it a little bit more and not just assume that. But what you can see again, all of the structures with no lone pairs are nonpolar. All the structures with one lone pair are polar, and then you have two of each for the ones that have more than one lone pair. So you have to sort of think about those and rationalize them. All right, so then we'll continue on with chapter 4 next time, that deals with bonding in covalent molecules. So we're done with shapes and polarity.
So when you have the extra electron or that you put on the central atom, does it matter where you place it?
I mean,
Because I saw
from the standpoint of a Lewis structure, no.
Okay,
From the standpoint of VSEPR, yes.
Okay.
You want to make sure. I mean, in some of the cases, it doesn't matter, but in other cases, like I said, especially if there's two lone pairs, then you need to make sure they're as far away from each other as possible. If it's the trigonal bipyramidal, they all go on the triangle. If it's
but
octahedral,
as far as Lewis structures are concerned, it does. Okay, because I saw like in one example you put them across from each
I
other.
just put them wherever they fit, basically.
Okay, perfect. Thank you, Professor.
Yes. And it can, because phosphorus is in the third row of the periodic table. So if you have your central atom in the third row of the periodic table or below, so anything past,
Okay, but
it's okay.
technically, like, isn't the right way to draw them?
No, it is. So P's in the third row. The first row, yeah, the first row is hydrogen, helium. So second row is, those are the ones that you can't. Let's see, the test of carbon, nitrogen, oxygen, fluorine.
Hello.
What's up? And then you have, the third row would be anything below that.
Um,
Yeah, no problem.
I have a question. So
I-
are you
I-
going to upload the completed version of the your slides on Canvas, right? Because,
I always do, yes.
okay, because I gotta study that and then register the exam on Dart Center.
Absolutely. All right, yeah, they'll be there in probably the next hour.
Is the test over? What's in the slide or in the textbook?
I mean, some of each, I try, like, the slides are designed to cover what I think is the most important information and kind of how you should approach it and think about it. Your best bet is to work the problems that we have in WebAssign. So, we have the weekly assignments. Ideally, by the end of the week, you'll know how to do all the problems from that week's assignments, and then we have, you have the ability to go back and review some of them. We have practice exam too that you can help. So it's, problem solving is really your best approach to take. The notes in the book can be helpful for, looking back at things and hopefully giving you some important information that helps guide your studying, but you really want to test yourself on your ability to do problems is the most important thing.
All right, thank you.
Okay, my question is, how do you know exactly which direction?
It's kind of like a tug of war. So imagine that each of the dipoles is, you're pulling on the center atom. And whichever one is the stronger pole, that's going to be, or the net direction of the pole is going to be the dipole. So it's sometimes hard to visualize,
Yeah.
but, and that's probably, I don't think we're going to ask those types of questions too much anyway. That usually at least the test questions are going to be focused on, is it polar or is it non-polar? As far as I know, we haven't, Professor Larson managed the test questions, so he would know more than I would, but I mean, I don't think they've changed much from year to year. Even this year, when we've gone to WebAssign, we've kept the test questions pretty much the same. And in the past, that was the distinction. Is it polar or non-polar? Not so much about the direction of polarity. Yeah.
You're the carbon. I was confused, how do you know when to put like the double bond?
Well, so that in that case, you could put the double bond on any of the three carbon oxygen bonds. So there would really be three resonance forms. So resonance is a situation where you have two or more Lewis structures that are equivalent, and you sort of draw all three of them as kind of like the real structure would be the average of those. So it doesn't really matter where you put it for just one of those resonance forms. And for VSEPR, it doesn't even matter if we have it at all. But for the truly correct Lewis structure, you would want to have all three resonance forms indicated, showing that the bond is not really between one carbon and one oxygen, but delocalized over all three of them. I believe it's the end of the following. So like Thursday or Friday, I have to look exactly how it's scheduled. There might be information about that. I'm not sure if it's in this syllabus or not, but I'm 99% sure it'll be hopefully following, but towards the end of the week.
Okay, so just email you and then how would I schedule?
So I think what happens, this is again, a new system for CASA too. I think I would, if, as long as the excuse is valid, which sounds like it will be, then I will give you, I think I have to do something with CASA to give you permission to register, and then you'll get information about how to do it after I put you on there.
Thank you.
No, not today.
Okay, I had questions about like how are we supposed to like, I mean, not memorize, but I guess learn this whole chart, or we're supposed to go through all of these and determine shape? Or we're supposed to just see AX3 and know automatic events like trigonal planar?
I mean, you're welcome to memorize it. That's one way to do it. I think like the way I kind of learned it was try to learn the five basic shapes that would be the number of total number of electron groups. And then if you just draw those and place the lone pairs, that can help you then figure out what the shape is. You have to become familiar with them, but just memorizing the table without really thinking about the shapes is not always the best or most satisfying way to do it.
Okay, and then again, how is this like, how are we looking at this? How is this one square print? Oh, no, I'm sorry, this one, how is this one trigonal bipyramidal?
Because there's five electron
Describe it
groups.
exact.
Well, I didn't. I don't know if I drew I don't think I actually drew the actual shape here, but this you can't. This is just again a Lewis structure that's not
Yeah.
trying to indicate a real shape or anything. It's just arranging the electrons. But it's AX5E0. So whenever you have five electron groups, that's going to be trigonal bipyramidal arrangement. And
Alright.
then there's no lone pairs, so that means the geometry and the electron group arrangement are both trigonal bipyramidal. And anytime there's zero lone pairs, it's
Okay.
nonpolar.
Zero, no, okay, non-polar, but if it's two different molecules, then it would be polar.
Two different atoms.
Atoms,
So if it was like PCl4F, so there's still five total atoms, but four of them are fluorine and one of them is chlorine, then you would expect it to be polar. But if
And
it's
then-
five identical things, in this case chlorine, then you would expect it to be nonpolar.
So what does trigonal mean? Like, will that help me?
Trigonal means triangle. So if you look at the actual way that the shape looks, it's
And bipyramidal means two pyramids?
yeah, we just started with it at the beginning of today. We didn't cover it last time, so you haven't had a lot of time to internalize it. But if you go back to like slide 1 or whatever, one of the first slides here, we call it trigonal bipyramidal because it's it's a triangle base with one above and one below, or maybe that picture is even easier. So it's three atoms in it. Three of them are in a triangle, one above, one below.
So triangle this way, and then bipyramidal, two pyramids on bottom and top.
Yeah. So imagine you just have a triangle with a flagpole sticking up and down.
Okay,
Yeah.
that makes sense. All right, thank you.
So. Yes, email me about something.
Yeah,
Remind me what it was.
it was about the charts. Which ones?
Oh, yeah. Okay, got it. Yeah.
Okay, so also I was wondering about the prefixes, like the ones that's like 10 to the third kilo.
Yeah, so technically speaking, if there's two questions on the exam from the review chapter, and like all of those would be fair game for those two questions, although
Okay.
the likelihood of you seeing that is not high because there's only two questions. when you get to the actual like chemistry material, you'll kind of see from the practice problems which ones are most